Hi, today we're going to do number 226, invert binary tree. So we're giving a root of a binary tree, invert it, and return that root. So we can see here 4, 4, 2, 2, 7, 1, 3, 6, 9. And here 4 is the same, 2 and 7 we switch, and then 1, 3. We switch the 3, 1 here, and also that it'll also be switched to go on this side as well, to go with 2 so for each one we just, and then 7, 6, 9 and switch. So we can see here, if we look at the smaller example here, 2, 1, 3, we just 2, 3, 1. And a good intuition we see that the smallest possible problem, we just reverse it and then do it for the entire problem. So we can, one way we can do it is using recursion, and that is using def for first search DFS. So here we can just, if the base case, if we go to an end, or if it's null, if node is null, return null. And then on our way up, we will want to swap left and right node and do this throughout the call stack of the problem. And after that, we just return root. So here, the time complexity is going to be O of n, since we're going to loop through the entire iteration of the tree. And also the space complexity, we're creating a call stack for the length, so it's also going to be O of n. Now, how else can we do DFS is to use a stack. So stack DFS, or you can also call it iterative. So here we create stack with initial root node as value, and then while the stack has a value, we want to pop one out and switch left and right node, and then we want to only add left or right node if not null. And then once we go through that, we have the solution and we can just return root. And then the same idea, since we're iterating through the entire root, and then we're also having the space complexity of adding the stack for the length of this root is going to be O of n for both, where n is the length of the root. And when iterating trees, we can also do BFS with queues. And here we basically do the same thing. So I'm just copying it, but instead of a stack, we create a queue. And since the recursion has the simplest solution, because the edge case is kind of built in, and here we have to handle it, I will go with the recursive DFS. So here, starting before, here we can do if root is not null, the base case, we return null. Now we want to swap it. So here, root dot left, root dot right equals root dot right, root dot left. And now we just call this function again. root dot left. And now we just return root. Great, so that's one way. So the other way is to create a stack. So it starts off the same. We're going to return, if it's null, we just return null. And then at the end, we want to return root. But now we create the stack. So const stack equals root, like that. And now we do a while loop, while stack dot length, while there's something in the stack, we want to get the current. And we pop it. Now we do the swap. And here you want to add a semicolon or else the swap syntax doesn't work. So current dot left, current dot right, swap the values. And now if there's a left value, you want to add it to the stack. Great, so that's the stack way. And then now we'll do it the queue way using BFS. So here it starts off the same. If there's nothing in the root, return null, and then at the end we want to return the root. So here we create the queue, const queue equals, and you can use this pre-built queue class, pass in the root, and now we do a while queue is not empty. We do the same idea, so we get the current equals queue dot pop, and then we swap them. And now we only add it to the queue if it has a value. Great. So those are the three ways we can invert the binary tree. So I like to think of it as the base problem and see what you need. You need to swap each one. So you can either do that recursively. So once you have the edge case, you return null, and then otherwise you just want to swap them up the call stack, or you can do a BFS with the queue and swap them as you go down each one, adding one only if that's a value, or you use a stack with the same idea where initialize the stack with the root and then swap them. If it has a value, you add the left and right to it. And that's all. Thank you.